So here's something to think about as you settle in tonight. Right now, wherever you are, you're surrounded by it. It's flowing through the walls around you, humming quietly in things you can't even see, keeping your phone alive, keeping the air moving, keeping the world ticking along in ways so constant and so invisible that you've probably gone your entire life without once stopping to really think about what it actually is. Electricity. It's maybe the most transformative thing human beings have ever harnessed, and yet, if someone asked you to explain it, really explain it from the beginning, how we figured it out, how we went from rubbing amber on fur to lighting up entire cities, most of us would struggle to get past the first few sentences. And that's okay. That's what tonight is for. We're going to walk through the whole story, slowly, from the very beginning. And I mean the very beginning. Not Edison, not Tesla, not even Benjamin Franklin. We're going much further back than that. Back to a time when electricity wasn't a science. It wasn't even a word. It was just a strange, inexplicable thing that happened when you rubbed certain objects together. A little spark, a tiny crackle, a pull that no one could explain. Let's start there. Let's start with amber. About 2,500 years ago, give or take, in the part of the world we now call Greece, there was a philosopher named Thales of Miletus. He lived around 600 BCE, and he was one of those restless minds who wanted to understand everything: why rivers flooded, what the stars were made of, whether the world had some fundamental substance at its root. He's sometimes called the first philosopher of Western civilization, which is a big title. But the reason he matters to us tonight is much simpler than that. Thales noticed something peculiar about amber. Amber, if you haven't held a piece, is fossilized tree resin. It's golden, translucent, warm to the touch, and the Greeks used it for jewelry and decoration. They called it electron. And Thales noticed, or at least he's credited with noticing, that if you took a piece of amber and rubbed it vigorously with a piece of fur or wool, it would attract small, light things, bits of straw, feathers, dust. They'd leap toward the amber as if pulled by some invisible hand. Now think about what that must have looked like to someone in 600 BCE. You rub a pretty stone, and suddenly it reaches out and grabs things without touching them. That's basically magic. Thales didn't have a framework for understanding what was happening. He didn't know about electrons, or charge, or atomic structure. He just knew that something was going on, something real and repeatable. And he was curious enough to write about it. Some historians think he believed the amber had a kind of soul, that the attraction was evidence of life within the stone, which is a beautiful idea, even if it's wrong. But here's the thing. He was observing a genuine electrical phenomenon. When you rub amber against fur, you're transferring electrons from the fur to the amber, giving the amber a net negative charge, and that charge creates an electric field strong enough to attract lightweight objects. Thales had no way of knowing any of that, but he saw the effect. He documented it. And that word, electron, his word for amber, would eventually give us the word electricity itself. And then, for a very long time, almost nothing happened. I mean that seriously. For roughly 2,000 years after Thales, the understanding of electricity barely advanced at all. People knew about the amber effect. They knew about lightning, obviously. Every culture had stories about lightning, usually involving angry gods. The Romans associated it with Jupiter. The Norse had Thor. And there were a few other scattered observations. The Romans, for instance, knew about torpedo fish, electric rays that could deliver a painful shock if you stepped on them or touched them. They even used them medicinally, if you can believe that. There are accounts of Roman physicians recommending that patients with gout stand on a live torpedo fish to numb the pain, which is simultaneously horrifying and kind of ingenious, because what they were really doing, without knowing it, was using bioelectricity as a crude form of nerve stimulation. But nobody connected the torpedo fish to the amber. Nobody connected either of them to lightning. These were all separate mysteries, unrelated, as far as anyone could tell. And that's an important thing to sit with for a moment, because it tells you something about how science actually works. We tend to think of scientific progress as this steady march forward, one discovery building neatly on the last, but the reality is messier than that. Sometimes a phenomenon is right there in front of people for centuries, millennia even, and nobody makes progress on it because they don't have the right questions, or the right tools, or the right framework for thinking about it. Electricity was hiding in plain sight for 2,000 years. It took until the late 1500s for someone to finally pick up the thread again. That someone was William Gilbert, and he's a fascinating character. Gilbert was an English physician, born in 1544 in Colchester, and he served as the personal doctor to Queen Elizabeth I. So he had status, he had resources, and he had an unusually rigorous mind for his era. In 1600, he published a book called De Magnete, On the Magnet. And while the title suggests it's mainly about magnetism, which it is, Gilbert also did something crucial for our story. He systematically studied the amber effect that Thales had noticed 2 millennia earlier, and he discovered that amber wasn't special. Lots of materials could be made to attract small objects after rubbing: glass, sulfur, various gemstones. He tested dozens of substances and cataloged which ones exhibited this attractive force and which ones didn't. He called materials that could be charged in this way electrics, directly from the Greek electron. And that's where our word comes from. William Gilbert coined it, or rather he Latinized it and gave it to science. But here's what's really clever about what Gilbert did. He also made a clear distinction between the amber effect, what we'd now call static electricity, and magnetism. Before Gilbert, people tended to lump them together. Amber attracts straw, magnets attract iron. Must be the same thing, right? Gilbert said no. He showed that they behaved differently. Magnets didn't need to be rubbed. The magnetic force worked through barriers. The electric force was affected by moisture and humidity. They were related in ways that wouldn't become clear for another 200 years, but they were not the same phenomenon. That distinction matters enormously because it meant electricity could be studied on its own terms, as its own thing, separate from magnetism. Gilbert gave it an identity. Now, Gilbert was working right at the dawn of what we call the scientific revolution. And after him, things started to pick up, slowly at first, then with increasing momentum. In the 1600s, a German named Otto von Guericke built what's generally considered the first electrostatic generator. Picture this. It was a ball of sulfur about the size of a child's head, mounted on an iron shaft so it could be spun. Von Guericke would spin the sulfur ball and press his dry hand against it, and the friction would build up a charge on the surface. He could then bring the charged ball near small objects and watch them dance toward it, or he could draw small sparks from it. It was crude, it was simple, but it was the first machine that could produce electricity on demand, rather than just rubbing a piece of amber by hand. That's a conceptual leap. You're going from observing a natural curiosity to building a device that creates the effect deliberately and repeatably. That's engineering, even in its most primitive form. And von Guericke noticed something else. something that must have been genuinely startling. He found that the attractive force could be transmitted along a linen thread. If he connected his charged sulfur ball to a thread and dangled a feather near the other end of the thread, the feather would be attracted from a distance. He was seeing electrical conduction. The charge was traveling along the thread. He didn't fully understand what he was seeing, but he documented it, and others would build on it. By the early 1700s, the study of electricity was becoming fashionable, and I mean that almost literally. It was becoming a form of entertainment. Traveling lecturers would tour Europe performing electrical demonstrations for paying audiences. They'd charge up glass tubes by rubbing them with silk, then use them to make sparks fly, make people's hair stand on end, attract bits of paper and leaf. One popular demonstration involved suspending a boy from silk ropes, silk being an insulator, though they didn't use that word yet, and then charging him up by touching him with an electrified glass tube. His face would glow faintly in the dark, his hair would stand straight up, and if someone approached with their hand, a visible spark would leap from the boy's nose. Audiences loved it. It was spectacular, it was mysterious, and it was, in a strange way, laying the groundwork for serious science, because it was getting people interested. It was making people ask questions. One of those people was Stephen Gray, an English dyer and amateur scientist, who in the 1720s and 1730s made a discovery that seems obvious in hindsight, but was genuinely revolutionary. Gray figured out that there were two kinds of materials when it came to electricity. Some materials allowed the electric virtue, as he called it, to flow through them easily. Others blocked it. He could transmit a charge along a brass wire for hundreds of feet, but a silk thread would stop it cold. We now call these conductors and insulators, and the distinction is fundamental to everything. Every wire, every circuit, every device you've ever used depends on this basic idea that some materials let charge flow and others don't. Gray didn't know about electrons. He didn't know what charge was, but he mapped out the behavior, and that map turned out to be remarkably accurate. Around the same time, a French chemist named Charles-François de Cisternay-Dufay, wonderful name, discovered something even more interesting. He found that there seemed to be two different kinds of electricity. If you rubbed glass with silk, you got one kind. If you rubbed resin with fur, you got another kind. And here's the key observation. Objects charged with the same kind of electricity repelled each other, while objects charged with different kinds attracted each other. Dufay called them vitreous and resinous electricity, from the Latin for glass and resin. This was the first hint that electrical charge comes in two flavors, what we now call positive and negative. And that idea, that there are two types of charge, and that like charges repel while opposite charges attract, is one of the most fundamental principles in all of physics. Dufay saw it in the 1730s, working with glass rods and bits of gold leaf in a Parisian laboratory. And it was right around this time, in the 1740s, that something happened in the Dutch city of Leiden that would change everything. A professor named Peter van Musschenbroek was experimenting with ways to store electrical charge. See, the problem with all the static electricity experiments up to this point was that the charge dissipated quickly. You'd rub your glass tube, build up a charge, and within moments it would leak away into the air. You couldn't accumulate it. You couldn't save it for later. Van Musschenbroek, along with a colleague named Andreas Cuneus, stumbled onto a solution almost by accident. They were trying to charge water inside a glass jar, and Cuneus, holding the jar in one hand while touching a charged conductor with the other, accidentally created a circuit through his own body. The shock he received was reportedly so violent that he said he wouldn't repeat the experiment for the entire Kingdom of France. What they had inadvertently invented was the Leiden jar, the very first electrical capacitor, a device that could store charge and release it all at once in a powerful burst. The Leiden jar was simple, a glass jar coated inside and out with metal foil, with a metal rod passing through the lid to contact the inner foil. You charged it up by touching the rod to an electrostatic generator, and the charge accumulated on the inner foil, held in place by the glass insulator, with an equal and opposite charge building on the outer foil. When you connected the inner and outer foils through a wire or through your body, as poor Cuneus discovered, all that stored energy discharged at once, and the amount of energy you could store was remarkable. People started connecting multiple Leiden jars together in what they called batteries. And yes, that's where the word comes from. A battery of jars, like a battery of cannons. With enough jars linked together, you could produce sparks several inches long, kill small animals, ignite gunpowder from across a room. Electricity had gone from a parlor trick to something genuinely powerful, and a little bit dangerous, and the person who would do more than anyone else to make sense of it all was a printer's son from Boston who had never attended a university in his life, Benjamin Franklin. A man who, by the time electricity captured his imagination in the mid-1740s, had already lived several lifetimes' worth of careers. He'd run away from an apprenticeship to his older brother's print shop in Boston, made his way to Philadelphia as a teenager with almost nothing in his pockets, taught himself to write by reverse engineering essays from a British literary magazine, built a printing business, published Poor Richard's Almanac, helped found a lending library, organized a volunteer fire company, and retired from active business at the age of 42, wealthy enough to spend the rest of his life doing whatever interested him most. And what interested him most, starting around 1746, was electricity. Now, Franklin didn't come to the subject as a trained natural philosopher. He had no university degree, no formal instruction in physics or mathematics. What he had was an extraordinarily sharp mind, a gift for clear thinking, and a complete lack of reverence for the way things had always been explained. When a traveling lecturer named Archibald Spencer came through Philadelphia demonstrating electrical tricks, sparks from Leiden jars, bits of metal leaf dancing on charged plates, all the usual showmanship, Franklin was captivated, not just by the spectacle, but by the questions underneath it. What was actually happening? What was this stuff? He got his hands on some basic equipment, including a glass tube for generating static charge, sent to him by a friend in London named Peter Collinson. And then he did what Franklin always did. He started experimenting, methodically, in his own home, writing down everything he observed. And within just a few years, he had developed a theory of electricity that was more coherent and more useful than anything that had come before. Here's the thing about the state of electrical knowledge in the 1740s. People had accumulated a lot of observations. They knew about conductors and insulators. They knew about the two types of charge that Dufay had identified, vitreous and resinous. They knew about attraction and repulsion. They had the Leiden jar, but there wasn't a unifying framework that tied it all together. It was a collection of facts without a theory, like having 1,000 puzzle pieces dumped on a table with no picture on the box. Franklin's great insight was deceptively simple. He proposed that electricity was a single fluid, not two different types, but one substance that existed in all matter. When an object had more than its natural share of this fluid, Franklin called it positively charged. When it had less than its natural share, he called it negatively charged. That's it. One fluid. And the difference between positive and negative was just whether you had an excess or a deficit. What Dufay had called vitreous and resinous weren't two different kinds of electricity. They were two states of the same thing. And think about what that means for understanding the Leiden jar. Franklin realized that when you charged the jar, you weren't creating electricity from nothing. You were moving it. The charge that accumulated on the inner foil was being drawn from somewhere, specifically from the outer foil through the glass, leaving the outer foil with a deficit. The total amount of electrical fluid in the system hadn't changed at all. It had just been redistributed. This was, in essence, the first clear statement of what we now call conservation of charge. Charge is neither created nor destroyed. It moves. Franklin also figured out something subtle about the Leiden jar that surprised everyone, including himself. He showed through clever experiments that the charge wasn't actually stored in the metal foils at all. It was stored in the glass. You could disassemble a charged Leiden jar, remove the inner foil, touch it, nothing. Remove the outer foil, touch it, nothing. But the glass itself retained the charge, and if you reassembled the jar with fresh foils, the shock was still there, waiting. The glass dielectric was doing the real work. That's a genuinely deep insight for someone working in a home laboratory in colonial Philadelphia in the 1740s. But of course, the experiment Franklin is most famous for is the one with the kite. And the story most people know about it is mostly wrong. So let's talk about what actually happened. The popular image is Franklin standing in a field, flying a kite in a thunderstorm, getting struck by lightning, and somehow surviving. That's not it. If lightning had actually struck his kite, Franklin would almost certainly have been killed. What he actually did, in June of 1752, was much more careful and much more clever. Franklin had already proposed, based on his experiments with pointed conductors, that lightning was electrical in nature, that it was the same phenomenon as the sparks from a Leiden jar, just vastly larger. This was a bold claim. Lightning was considered a supernatural force by many people, an act of God, not something that could be captured in a bottle. Franklin proposed a way to test it. Put a pointed metal rod on top of a tall structure, insulate it from the ground, and see if it would draw electrical charge from storm clouds. He described this experiment in letters to Peter Collinson, which were published in London and translated into French. And here's something that's often forgotten. The experiment was actually performed successfully in France before Franklin ever flew his kite. In May of 1752, a retired soldier named Thomas Francois Dalibard, following Franklin's published instructions, set up an iron rod 40 feet tall in a garden near Paris. When a thunderstorm passed over, a man named Coiffier, who was watching the apparatus, drew sparks from the rod with a brass wire. It worked. Lightning was electrical. The news electrified, if you'll pardon the pun, the scientific world. The King of France sent his personal congratulations. Franklin, not yet knowing about Dalibard's success, came up with the kite as an alternative approach, since Philadelphia didn't have a suitably tall building or steeple at the time. He flew a silk kite, not paper, silk, because it would survive rain, with a pointed wire at the top, connected by a wet hemp string to a silk ribbon he held in his hand. The silk ribbon was the insulator. At the junction of the hemp string and the silk ribbon, he tied a metal key. The idea was that if the storm clouds were electrified, charge would travel down the wet string to the key, where he could detect it. And that's exactly what happened. He noticed the loose fibers of the hemp string standing erect, repelling each other, a sure sign of electrical charge. He touched his knuckle to the key and got a spark. He then charged a Leiden jar from the key, proving that the charge from the sky behaved identically to the charge from his laboratory generators. Lightning was electricity, the same stuff that made amber attract feathers, that shocked poor Cunius through his Leiden jar, was the same force that split trees and set buildings on fire. And Franklin immediately turned this knowledge into something practical. That was always his instinct, not just to understand, but to use. He invented the lightning rod, a simple pointed metal conductor mounted on the roof of a building, connected by a wire to the ground. The idea was that the pointed tip would silently draw charge from the air during a storm, preventing the massive buildup that leads to a lightning strike. And if lightning did strike, the rod would give it a safe path to ground, protecting the building. It worked beautifully. Within a few years, lightning rods were being installed on buildings across Europe and the American colonies. Churches, which had been particularly vulnerable because of their tall steeples, and which had suffered devastating fires for centuries, could finally be protected. Some clergy initially objected, arguing that deflecting lightning was interfering with divine will, but pragmatism won out pretty quickly when the church next door stopped burning down. Franklin's contributions to electrical science went beyond any single experiment. His terminology shaped the field permanently. Positive, negative, conductor, battery, charge. These are all Franklin's words, or words he repurposed so effectively that they stuck. His single fluid theory, while not exactly right in modern terms, we now know electricity involves the movement of electrons, which carry negative charge, so current actually flows in the opposite direction from what Franklin assumed. His framework was so useful and so internally consistent that it dominated electrical thinking for decades. And his convention for positive and negative, somewhat ironically, is still the one we use today. When you look at a circuit diagram and see current flowing from positive to negative, that's Franklin's convention, even though the electrons are actually moving the other way. It's one of those historical quirks that's baked so deeply into the language of electrical engineering that it would be more trouble to change it than to just live with it. Now, while Franklin was doing his work in Philadelphia, electrical research was accelerating across Europe too. And one of the most important developments of the second half of the 18th century came from an unlikely source. Not a physicist, not an engineer, but an anatomist in Bologna, Italy, named Luigi Galvani. Galvani was a professor of anatomy at the University of Bologna, and in 1780, he noticed something strange while dissecting frogs. When a metal scalpel touched the leg of a dead frog near an electrostatic machine that happened to be sparking nearby, the leg twitched, violently, as if the frog were alive. This fascinated Galvani. He spent years investigating, trying different conditions, different metals, different configurations. He found that he could make frog legs twitch by touching them with two different metals simultaneously, say, a copper hook and an iron plate. No electrostatic machine needed. He concluded that the electricity was coming from the frog itself, that animal tissue contained an inherent electrical force, which he called animal electricity. It was a reasonable interpretation. After all, the torpedo fish that the Romans had known about was proof that living creatures could produce electricity. Maybe all animal tissue had this property, but not everyone agreed with Galvani's interpretation. And the person who disagreed most loudly, most persistently, and ultimately most productively was a physics professor at the University of Pavia. about 120 miles northwest of Bologna. His name was Alessandro Volta, and the argument between these two men, the anatomist and the physicist, the frogman and the metal man, would lead directly to one of the most important inventions in the entire history of technology. Because Volta believed the electricity wasn't coming from the frog at all. He thought the frog leg was just a sensitive detector, and that the real source of the electricity was the contact between the two different metals. The frog was the instrument, not the generator. And to prove it, Volta set out to produce electricity from metals alone, without any animal tissue whatsoever. What he built, in the closing months of the year 1799, sitting in his laboratory in Pavia as the 18th century drew to a close, was something the world had never seen before. A device that could produce a steady, continuous flow of electrical current, not just a single sudden spark like a Leiden jar, but a sustained river of charge that kept flowing as long as the device held together. He called it the crown of cups, though history would remember it by a different name. Volta actually built two versions of his device. The first was literally a row of cups, wine glasses or small bowls filled with brine or dilute acid, with strips of two different metals dipping into each cup and connected in series. Copper and zinc were his preferred pairing. One strip of copper and one strip of zinc went into each cup, and then you'd connect the copper strip in one cup to the zinc strip in the next cup with a little arc of metal wire, and so on down the line. It worked. You could feel a tingle if you touched both ends, but it was bulky, messy, and hard to transport. Imagine trying to carry a dozen cups of salt water across a room without spilling. So Volta came up with something more elegant, and this is the version that changed everything. He took small discs of copper and small discs of zinc, each maybe the size of a coin, and he stacked them in a vertical column. Copper, zinc, then a piece of cardboard or cloth soaked in brine or acid, then copper, zinc, another wet disc, and so on, alternating all the way up. Just a neat little tower of metal and wet cardboard. That's it. That's the whole thing. And when you touched a wire to the bottom disc and another wire to the top disc, you got a continuous flow of electric current. Not a spark, not a single jolt. A steady, persistent stream of charge moving through the wire, as long as the chemical reactions inside the pile kept going. He announced it in a letter to Sir Joseph Banks, the president of the Royal Society in London, dated March 20th, 1800. And the scientific world absolutely lost its mind. Think about what Volta had just given them. For the entire history of electrical experimentation, going all the way back to those friction machines and Leyden jars, researchers had only ever had access to static electricity. Brief, violent, hard to control. You'd charge something up, discharge it in a single crack, and then you'd have to start all over again. It was like trying to study water by throwing individual cups of it against a wall. But now, suddenly, here was a faucet. Here was a source you could turn on and leave on. You could run experiments that lasted minutes, hours, as long as your pile held out. And that changed absolutely everything about what was possible. The voltaic pile. That's what people started calling it. And that's where we get the word volt as a unit of electrical potential. The voltaic pile wasn't powerful by modern standards. We're talking about maybe a few volts from a modest stack. But it was reliable, it was reproducible, and it was steady. And within weeks of Volta's letter reaching London, researchers across Europe were building their own piles and discovering things that would have been completely impossible with static electricity alone. Here's what's really fascinating about the timing. Volta published in 1800, the very first year of the 19th century. And the 19th century would turn out to be the century of electricity. Almost everything we think of when we think about electrical technology, batteries, electromagnets, generators, motors, telegraphs, telephones, electric light, power stations, all of it came in the 100 years after Volta's letter. It's as if he opened a door and an entire civilization walked through it. The first major discovery came almost immediately. Just 6 weeks after Volta's letter was read at the Royal Society, 2 English chemists named William Nicholson and Anthony Carlisle got their hands on a voltaic pile and did something simple but profound. They connected wires from both ends of the pile and dipped the other ends of those wires into a container of water. And the water started to bubble. Gas was forming at both wire tips. At one end, hydrogen, and at the other, oxygen. They had split water into its component elements using electricity. This process would later be called electrolysis, and it was the first clear demonstration that electricity and chemistry were deeply, intimately connected. That electrical force could break apart the very molecules that made up matter. Now, that might sound like a neat laboratory trick, but let's talk about why it matters. Because a young man named Humphrey Davy, working at the Royal Institution in London, took electrolysis and ran with it in the most spectacular way. Davy was one of those figures who seems almost unfairly talented, charismatic, brilliant, a genuinely gifted public lecturer who packed audiences into his demonstrations the way rock stars fill arenas. He was also, it should be said, not always the easiest person to work with. But his scientific instincts were extraordinary. Davy realized that if electricity could decompose water, maybe it could decompose other substances too. Substances that no other method had been able to break apart. There were materials that chemists strongly suspected were compounds, mixtures of simpler elements, but nobody had ever been able to separate them. Caustic potash, for instance, what we now call potassium hydroxide. Chemists were pretty sure it contained an unknown metal, but no amount of heating or chemical reaction had ever managed to isolate it. In October of 1807, Davy built a massive voltaic pile, much bigger than anything Volta had used, and passed its current through a chunk of moistened caustic potash, and tiny globules of a shiny silvery metal appeared at one of the electrodes. They were so reactive that some of them burst into flame on contact with air. Davy had just discovered potassium, an element that had never been seen before in its pure form in all of human history, because it's so reactive that it never exists in nature by itself. His laboratory assistant later reported that Davy was so excited he literally danced around the room. Within days, he had isolated sodium using the same technique. And over the following years, he and others used electrolysis to discover barium, strontium, calcium, magnesium, element after element pulled from compounds that had resisted every other method of analysis. Electricity wasn't just a curiosity anymore. It was a tool, a key that could unlock the fundamental structure of matter. But here's the thing. And this is where the story takes a turn that I find endlessly compelling. While Davy was using electricity to do chemistry, someone else was about to discover that the relationship worked in the other direction too. That electricity and magnetism, which everyone had always considered to be completely separate phenomena, were actually two faces of the same coin. And the person who stumbled onto this connection was a Danish physicist named Hans Christian Ørsted. Ørsted had been teaching a class at the University of Copenhagen in the spring of 1820. There's some debate about exactly how it happened, whether it was a planned demonstration or a genuine accident, but the story that's come down to us is that Ørsted was running current from a voltaic pile through a wire during a lecture, and he happened to notice that a compass needle sitting on the table nearby moved. Not a lot, just a little twitch. But it moved when the current was on, and it stopped when the current was off. Now, you have to understand how strange this was. Magnetism was something that came from lodestones, from iron. It had nothing to do with electricity, or at least that's what everyone believed. There was no theoretical reason to expect a wire carrying an electric current to affect a compass. And yet, there it was. The needle moved. Ørsted spent the next few months carefully investigating the effect. He confirmed that a wire carrying current created a magnetic field around itself, not pointing toward the wire or away from it, but circling around it like invisible rings wrapped around the wire. If you pointed your thumb in the direction the current was flowing, the magnetic field curled around in the direction your fingers would curl. It was a completely new kind of relationship between two forces that humanity had known about for thousands of years without ever suspecting they were connected. He published his results in July 1820 in a short Latin pamphlet that he sent to scientific societies across Europe. And the reaction was electric, if you'll forgive the pun, because this wasn't just a new fact. This was a new category of fact. It meant that the universe was more deeply interconnected than anyone had realized. Forces that seemed separate were actually linked. And if an electric current could create magnetism, well, could magnetism create electricity? That question would consume the next decade of research. But before we get there, let's stay with 1820 for a moment, because the discoveries came fast and furious that year. Within weeks of hearing about Ørsted's experiment, a French physicist named André-Marie Ampère began a series of brilliant investigations. Ampère showed that two parallel wires carrying current would attract each other if the currents flowed in the same direction, and repel each other if the currents flowed in opposite directions. Think about that. Two wires, no magnets anywhere, and yet they're pushing and pulling on each other just because of the current flowing through them. Ampère worked out the mathematical laws governing these forces, and he proposed that magnetism itself, all magnetism, even the magnetism of a permanent iron magnet, was ultimately caused by tiny electric currents circulating within the material. He was essentially right, though it would take another century and the development of quantum mechanics to fully explain why. Ampère's work gave us the unit of current that bears his name, the ampere, or amp. So now, we've got volts from volta and amps from ampere, two of the most fundamental units in electrical engineering, both named for men working in this extraordinary period, right at the start of the 19th century. And then, there was a man who took Ørsted's discovery in a more practical direction. Within months of the announcement, a French instrument maker and part-time physicist named François Arago showed that you could magnetize an iron needle by wrapping it in a coil of current-carrying wire. And an English experimenter named William Sturgeon took that idea further in 1825 by bending a piece of iron into a horseshoe shape, wrapping it with wire, and passing current through the coil. When the current was on, the iron became a powerful magnet, strong enough to lift objects many times its own weight. When the current was off, the magnetism largely disappeared. Sturgeon had invented the electromagnet. This is one of those inventions that sounds simple, but is actually revolutionary. Because now you had controllable magnetism. You could turn it on and off. You could make it stronger by adding more coils or more current. You could put it exactly where you wanted it. And controllable magnetism turns out to be the beating heart of almost every electrical machine that would follow. Motors, generators, telegraphs, relays, transformers, hard drives. All of them depend on electromagnets. But the biggest question was still hanging in the air, unanswered. Ørsted had shown that electricity could create magnetism. Could you reverse the trick? Could magnetism create electricity? Several people were chasing this problem, but the one who cracked it, and the story of how he cracked it, and who he was, and where he came from, is one of the greatest stories in the entire history of science. His name was Michael Faraday, and he had started his career as Humphrey Davy's laboratory assistant at the Royal Institution. In fact, Davy had hired him after Faraday, a young bookbinder's apprentice with almost no formal education, attended one of Davy's public lectures and sent him a beautifully bound set of notes afterward. Faraday was largely self-taught, had virtually no mathematical training, and came from a working-class family in South London. He should not, by any conventional measure of the time, have become one of the greatest experimental physicists who ever lived. But he had something that no amount of formal education can reliably produce, an almost supernatural intuition for how the physical world actually behaves. Faraday didn't think in equations. He thought in pictures. He imagined forces as lines stretching through space, curving around magnets, reaching out from charged objects like invisible fingers. And while the mathematically trained natural philosophers of his era sometimes looked down on this, they wanted rigorous algebra, not mental imagery, it turned out that Faraday's way of seeing the world was not just valid, it was prophetic. His pictures would eventually become the formal mathematics of field theory, the very foundation of modern physics. But that vindication was decades away. In the 1820s, Faraday was just a brilliant, dogged experimentalist with a notebook and a question that wouldn't leave him alone. Could magnetism create electricity? Think about why this mattered so much. Volta's pile gave you current, yes, but it was chemical. You had to keep replacing the metal plates, refreshing the acid. It was expensive, messy, and it didn't scale well. If you could somehow use a magnet to generate a continuous electric current, well, that would change everything. You'd have a way to produce electricity mechanically, with motion, with a spinning wheel, or a flowing river, or a steam engine. You'd have a bridge between the mechanical world and the electrical world, and that bridge, once built, would carry civilization across it. Faraday wasn't the only one who sensed this. Across the Atlantic, an American named Joseph Henry was working on the same problem, and in fact, Henry may have observed the key effect slightly before Faraday did. But Faraday published first in 1831, and in science, sometimes unfairly, publication is what counts. Henry was generous about it, actually. He acknowledged Faraday's priority, and the two maintained a respectful relationship. But it's worth knowing that the discovery was, in a sense, in the air. Multiple people were circling it. The physics was ripe. So here's what Faraday did. He took a ring of soft iron, imagine a donut shape, maybe 6 inches across, and he wound 2 separate coils of wire around it, one on each side. The 2 coils were electrically independent. One coil he connected to a battery. The other he connected to a galvanometer, which is just a sensitive device for detecting current. Basically, a compass needle near a wire. His idea was straightforward. If electricity in the first coil creates magnetism in the iron ring, and if that magnetism can create electricity, then the second coil should show a current. Makes sense, right? Magnetism as the intermediary, the go-between, passing the message from one coil to the other. And here's what happened. When he connected the battery, the galvanometer needle twitched, just a brief flick. Then it settled back to 0. While the current flowed steadily through the first coil, the second coil showed nothing. Nothing at all. But then, and this is the crucial moment, when he disconnected the battery, the needle twitched again in the opposite direction. Then back to zero. Now, a lesser experimentalist might have been disappointed. You're looking for a steady current and all you get is two tiny twitches? But Faraday understood immediately what he was seeing. The second coil didn't respond to magnetism. It responded to changing magnetism. It was the change, the turning on, the turning off, the increase, the decrease, that induced the current. A steady magnetic field, no matter how strong, produced nothing, but a magnetic field in motion, a field that was growing or collapsing, that created electricity. This is electromagnetic induction, and it is arguably the single most consequential discovery in the entire history of electrical engineering. Let that sink in for a moment. Every generator on Earth works because of this principle. Every transformer, every induction motor, the power plant that's keeping your lights on right now, wherever you are. It works because a magnetic field is changing inside a coil of wire, exactly the way Faraday first observed it on August 29, 1831, in his basement laboratory at the Royal Institution. He didn't stop with the iron ring. Over the following weeks and months, Faraday explored the effect from every angle he could think of. He showed that you could induce a current by plunging a bar magnet into a coil of wire, and that pulling it back out induced a current in the opposite direction. No battery needed at all, just a magnet and motion. He built a simple device where a copper disc spun between the poles of a magnet, and it produced a steady current. This was, in a very real sense, the world's first electrical generator. He called it a new electrical machine. It was crude, inefficient, and produced barely enough current to measure. But the principle was there, complete and correct. And here's what's really beautiful about Faraday's way of thinking. He described all of this in terms of what he called lines of force. He imagined magnetic lines of force filling the space around a magnet, curving from North Pole to South Pole. When a wire cut across those lines, moved through them, a current was induced. The more lines you cut per second, the more current you got. This is not how a mathematician would describe it, and Faraday's contemporaries sometimes found his language frustratingly imprecise. But he was right. He was seeing something real. Those lines of force that he imagined are what we now call magnetic field lines, and the rate at which a conductor cuts through them is directly proportional to the induced voltage. Faraday had the physics exactly right, expressed in the language of pictures rather than symbols. He also discovered something else during this period that's easy to overlook but enormously important: self-induction. When you change the current in a coil, the changing magnetic field of that coil induces a voltage in itself, opposing the change. It's as if the coil resists being changed. This is why when you flip a switch on a circuit with a big coil in it, the current doesn't jump instantly to its full value. It ramps up, fighting against its own self-induced resistance. And when you try to turn it off, the collapsing field generates a voltage spike that can arc across the switch contacts. If you've ever seen a little spark when you unplug something with a motor in it, that's self-induction. Faraday's ghost still playing tricks. Joseph Henry, over in America, actually explored self-induction in considerable depth, and the unit of inductance, the Henry, is named after him. It's one of those nice historical balances. Faraday gets the farad, the unit of capacitance. Henry gets the Henry, the unit of inductance. Both men deserved far more recognition than any single unit could provide. Now, Faraday continued working for decades after 1831. He investigated the relationship between electricity and light, and in 1845 he showed that a magnetic field could rotate the plane of polarization of light passing through glass. This was the first experimental evidence that light and electromagnetism were connected, a clue that would eventually lead to one of the most profound unifications in all of physics. But we'll get to that. What matters right now is the practical consequence of induction. Because once you know that a changing magnetic field creates electricity, and once you have electromagnets that you can control, you have all the ingredients for two machines that would reshape the world: the generator and the motor. Think about a generator. At its simplest, it's a coil of wire spinning inside a magnetic field. As the coil rotates, it cuts through the magnetic field lines and a current is induced. The mechanical energy of spinning gets converted into electrical energy. That's it. That's the whole trick. You can spin the coil with a water wheel, a steam turbine, a windmill, a diesel engine, anything that rotates, and out comes electricity. A motor is the same machine running in reverse. You feed current into a coil sitting in a magnetic field, and the magnetic forces push the coil around, creating rotation. Electrical energy in, mechanical energy out. Generator and motor are twins, mirror images of each other, and both are children of Faraday's discovery. But here's the thing. Knowing the principle and building a practical machine are very different challenges. Faraday's spinning disk generator was a proof of concept, not a power source. It produced tiny currents at low voltages. Making generators and motors that could do real work, that could light a city or drive a factory, took decades of engineering refinement by dozens of people whose names most of us have never heard. Inventors like Hippolyte Pixii in Paris, who built one of the first hand-cranked generators with a commutator in 1832, or the Belgian engineer Zenobe Gramme, who in 1871 built the Gramme dynamo, the first generator efficient enough to be commercially useful. Gramme's machine was a revelation. It could produce smooth, steady current, and it was efficient enough that you could actually use it to power things. Arc lamps, electroplating baths, industrial processes. And there's a wonderful story about the Gramme dynamo that perfectly illustrates the generator-motor duality. At the Vienna World Exhibition in 1873, a workman accidentally connected a wire from a running Gramme dynamo to a second Gramme dynamo that was just sitting there. The second machine immediately began to spin. It had become a motor, driven by the electricity from the first. This was apparently one of the first clear public demonstrations that the same machine could work both ways, and it caused enormous excitement. People suddenly saw that you could generate electricity in one place and use it to create motion in another. You could transmit mechanical power through a wire. That idea, transmitting power over a distance, was about to become the central obsession of the electrical age. Because it's one thing to generate electricity right next to the machine you want to run. It's quite another to generate it miles away and send it down a wire to a distant city. And the story of how that problem got solved, the fierce technical and personal battles it ignited, and the two towering figures who came to embody opposite sides of the argument. That story is coming. One of those figures was already famous by the early 1880s, a relentless American inventor with a laboratory in Menlo Park, New Jersey, who had just astonished the world by making a practical incandescent light bulb. His name was Thomas Edison, and he was absolutely certain he knew the right way to deliver electricity to the masses. The other figure was younger, less known, recently arrived in America from Europe with almost nothing in his pockets and a head full of ideas that most established engineers thought were impossible. His name was Nikola Tesla, and the ideas crackling around inside his mind were going to change the world in ways that Edison, for all his brilliance, simply could not see coming. Let's talk about Tesla for a moment. Because his story is one of the most extraordinary in the history of engineering, and it starts in a place most people wouldn't expect. Tesla was born in 1856 in a small village called Smiljan, in what was then the Austrian Empire, modern-day Croatia. His father was a Serbian Orthodox priest, his mother an inventor of small household tools who never learned to read. Tesla later credited her with giving him his love of making things. As a young man, he studied engineering in Graz, Austria, and it was there, in a physics lecture, that the seed of his great idea was planted. His professor was demonstrating a Graham dynamo, that same type of machine from the Vienna exhibition, running it as a motor. And the motor was sparking badly at the commutator, those mechanical brushes that keep the current flowing in the right direction. Tesla raised his hand and suggested that maybe you could build a motor that didn't need a commutator at all. His professor reportedly told him that what he was proposing was essentially a perpetual motion machine. Impossible. But the idea wouldn't leave him alone. Here's the thing you need to understand about why the commutator mattered so much, and why getting rid of it was such a radical thought. Remember how direct current works. It flows in one direction, steady and constant, like water through a pipe. That's what Edison's entire system was built around. DC. Every generator, every motor, every light bulb in Edison's vision ran on direct current. And to make a DC motor spin smoothly, you need that commutator, a rotating switch that keeps flipping the current direction inside the motor at just the right moment, so the magnetic forces keep pushing the rotor around instead of locking it in place. It works, but it's a mechanical compromise. The brushes wear out, they spark, they waste energy, and they limit how fast and how powerful you can make the motor. What Tesla envisioned was something fundamentally different. Instead of using direct current and mechanically switching it, what if you used a current that switched direction on its own, alternating current? And what if you designed the motor so that those alternations naturally created a rotating magnetic field? Think about it like this. Imagine you're standing in the middle of a circle of people, and each person is holding a flashlight. If they all turn their flashlights on and off in sequence, one after another around the circle, the bright spot appears to rotate around you, even though no one is actually moving. That's essentially what a rotating magnetic field does. You arrange multiple coils of wire around the motor. You feed them alternating currents that are slightly out of step with each other, out of phase, as engineers say. And the magnetic field inside the motor appears to spin. Drop a magnetized rotor into that spinning field, and it gets dragged along, spinning smoothly and powerfully with no brushes, no commutator, no sparking. It's elegant. It's beautiful, really. Tesla reportedly had the complete vision for this motor come to him during a walk in a park in Budapest in 1882. He was strolling with a friend, reciting poetry. Goethe's Faust, of all things, when the idea crystallized, fully formed in his mind. He grabbed a stick and drew diagrams in the dirt. He later said the image was so vivid, it was like looking at a real machine. Now, whether that story is perfectly accurate or slightly embellished by Tesla's own considerable flair for drama, the core fact is real. By the early 1880s, Tesla had conceived of the polyphase alternating current motor, and he knew it could work. But knowing something can work and getting anyone to care are two very different problems. Tesla worked briefly for Edison's company in Paris, then came to America in 1884, arriving in New York with a few cents in his pocket, a letter of introduction, and his ideas. He went to work for Edison directly, and by most accounts, the two men did not get along. Edison was a pragmatist, a tinkerer, a man who famously said genius was 1% inspiration and 99% perspiration. He tried thousands of materials for his light bulb filaments. He built things, tested them, broke them, tried again. Tesla was more of a theorist, a visualizer. He could design entire machines in his head, rotate them, test them mentally, and predict their performance before ever touching a tool. They were oil and water. Tesla left Edison's employ after a dispute. The details are murky, possibly involving a promised bonus that never materialized, and spent a miserable period digging ditches for a living. But eventually, through a series of connections, he found backers, set up his own laboratory, and in 1887 and 1888, he built working prototypes of his AC motor and filed a string of patents. In May of 1888, he presented his work to the American Institute of Electrical Engineers, and the engineering world took notice. And here's where the story gets really consequential, because one particular person in that world was paying very close attention. George Westinghouse was a successful industrialist, already famous for inventing the railway air brake, and he had been investing heavily in alternating current technology. Westinghouse understood something that Edison either couldn't see or refused to accept. AC had a massive practical advantage for power transmission over long distances, and this is the heart of the whole war of currents. So let's slow down and really understand why. When you send electricity through a wire, some of that energy gets lost as heat. The wire has resistance, and the current flowing through it generates waste heat. That's just Ohm's law and Joule heating, basic physics. The amount of power you lose depends on the current squared times the resistance. That squared part is crucial. If you double the current, you quadruple the losses. So if you want to send a lot of power a long way without losing most of it to heat, you desperately want to keep the current low. But here's the catch. Power equals voltage times current. So if you keep the current low, you need to raise the voltage to transmit the same amount of power. Think of it like water in a hose. You can deliver a lot of water either by using a fat hose with a gentle push or a thin hose with enormous pressure. High voltage is like high pressure. It lets you push the same power through thinner wires with less waste. So the trick to long-distance power transmission is generate electricity, step the voltage way up for the journey through the wires, then step it back down to safe, usable levels at the other end. And this is where alternating current had its killer advantage. Transformers, devices that step voltage up or down, work only with alternating current. They rely on changing magnetic fields to induce current from one coil to another, and direct current, by definition, doesn't change. It just sits there at a constant level. You can't easily transform DC voltage. With Edison's DC system, you were basically stuck with whatever voltage you generated, and for safety reasons, Edison was generating at about 110 volts. That meant his power plants could only serve customers within about a mile, maybe a mile and a half, before the losses in the wires became unacceptable. Every neighborhood needed its own power station. It worked. Edison's Pearl Street station in Lower Manhattan, which opened in September of 1882, was a genuine marvel, powering lights for about 85 customers in a small radius. But scaling it to an entire city, let alone a country, was going to require power plants on practically every block. Westinghouse saw that AC, with transformers, could solve this completely. Generate power at moderate voltage, step it up to thousands of volts for transmission, send it miles and miles through relatively thin, cheap wires with minimal loss, then step it back down at the destination. One large, efficient power plant could serve an enormous area. It was economically and technically superior for any kind of widespread electrical grid. And now, with Tesla's AC motor patents, Westinghouse had the missing piece. Before Tesla, AC could power lights just fine, but there was no good AC motor for running machinery. Tesla's polyphase induction motor changed that. Westinghouse licensed Tesla's patents in 1888 for a reported $60,000 plus royalties, a fortune at the time, and began building out an AC power system to compete directly with Edison. Edison fought back, and this is where the story takes a dark turn. Unable to win the argument on pure engineering merits, Edison launched what can only be described as a fear campaign against alternating current. He sponsored public demonstrations where animals, dogs, calves, even eventually a horse, were electrocuted with AC to show how dangerous it was. His associates helped develop the electric chair, which used alternating current, specifically so that AC would be associated with death in the public mind. Edison reportedly wanted people to call being electrocuted being Westinghoused. It was ruthless, manipulative, and ultimately unsuccessful, but it was a real and ugly chapter in engineering history. People died in those demonstrations, animals certainly, and the broader campaign created genuine public fear. But the engineering reality was stubborn. A C was simply better for transmission, and the demonstration that settled the argument once and for all came at a place you might not expect: Niagara Falls. For years, engineers and investors had been debating how to harness the enormous power of the falls. An international commission was formed, and after evaluating proposals from all over the world, they chose the Westinghouse AC system, using Tesla's polyphase designs. The Edward Dean Adams Power Plant began operation in 1895, generating electricity from the force of falling water and transmitting it 26 miles to the city of Buffalo, New York. It worked beautifully. The lights came on in Buffalo, the factories hummed, and the war of currents was effectively over. A C had won. Now I want to be fair to Edison here, because history has sometimes painted him as simply wrong, and that's too simple. Edison was an extraordinary engineer and innovator. His DC system worked perfectly well for the application he designed it for: dense urban lighting in a small area. His Pearl Street station was a masterpiece of integrated system design, from the generators to the wiring to the meters to the light bulbs. And DC never went away entirely. It found its niche in applications where you need steady, reliable current, like electroplating, battery charging, and eventually electronics. Your phone runs on DC right now. But for the big problem, the problem of building an electrical grid that could serve millions of people across vast distances, alternating current was the right answer, and Tesla and Westinghouse were the ones who proved it. There's a bittersweet coda to Tesla's part in this story. Despite the enormous value of his patents, Tesla eventually tore up his royalty contract with Westinghouse, reportedly because Westinghouse was in financial difficulty, and Tesla felt a sense of loyalty to the man who had believed in him. That decision cost Tesla millions, possibly hundreds of millions in today's money. He spent his later years increasingly eccentric and isolated, living in hotel rooms in New York, feeding pigeons, and dreaming of inventions: wireless power transmission, death rays, earthquake machines that ranged from visionary to fantastical. He died in 1943, largely alone. The unit of magnetic flux density, the Tesla, was named in his honor in 1960. It's a small consolation for a man whose ideas literally power the modern world. But the triumph of AC at Niagara Falls didn't just settle a business rivalry. It established the basic architecture of the electrical grid that still exists today. And it opened the door to something even bigger: Because once you could transmit power over long distances efficiently, you could start thinking about connecting power plants together, sharing loads, building redundancy into the system. You could start thinking about a network. And the person who began thinking most clearly about what that network should look like, how to manage the staggering complexity of generating and distributing electricity across an entire continent, was a man named Samuel Insull, who had actually started his career as Edison's personal secretary. Insull moved to Chicago in 1892 to run a small electric utility, and what he built there over the next 3 decades would become the template for the modern electrical utility as we know it. Insull is one of those figures who doesn't get nearly enough attention in the popular telling of the electricity story, probably because he doesn't fit neatly into the hero or villain categories we like. He was both, depending on when you caught him. But in terms of sheer impact on how electricity actually reaches your home, your office, the hospital down the street, Insull might matter more than Edison or Tesla because he figured out the business model. Here's the thing about the 1890s. Even after AC won the current wars, even after Niagara Falls proved you could transmit power over real distances, the actual experience of being an electricity customer was still pretty rough. Most cities had dozens of tiny competing electric companies, each running its own generators, its own wires, its own voltage standards. If you lived on one block, you might have service from one company. Your neighbor across the street might have a different company, or no service at all. The reliability was terrible, outages were constant, and the price was astronomical. Electricity was a luxury for the wealthy, for department stores, for fancy hotels. The average working family in 1895 couldn't dream of affording it. Insull looked at this chaos and saw something that nobody else seemed to see clearly. He understood that electricity was what economists would later call a natural monopoly, an industry where it makes no sense to have multiple competing providers because the infrastructure costs are so enormous that duplication is pure waste. You don't want 5 different companies each stringing their own power lines down the same street. You want one set of wires, one coordinated system, and you want it regulated so the company that runs it can't gouge people. Insull didn't invent this idea from scratch, but he was the first person to really build it, to prove it worked, and to scale it. When he arrived in Chicago, his company, Chicago Edison, later Commonwealth Edison, was one of about 20 electric companies serving the city. Within a decade, he'd bought or driven out nearly all of them. And he did it not through dirty tricks, though he wasn't above political maneuvering, but primarily by being better. He was relentless about efficiency. He understood something called the load factor, and this is worth pausing on because it's one of those concepts that sounds dry, but actually explains why your electricity is affordable. Think about it this way. A power plant has a certain maximum capacity. Say it can produce 100 megawatts. But demand for electricity isn't constant throughout the day. At 3 in the morning, almost nobody's using power. At 6 in the evening, when everyone's cooking dinner and turning on lights, demand spikes. If your plant is sized for the peak, then most of the time it's sitting there barely working, and all that expensive equipment is idle. The load factor is the ratio of average demand to peak demand. A low load factor means your plant is underutilized, which means each unit of electricity you actually sell has to bear a larger share of your fixed costs, which means higher prices. Insull was obsessed with raising the load factor, and his insight was brilliant in its simplicity. If you could diversify your customer base, you could smooth out the demand curve. Residential customers peak in the evening. Factories peak during the day. Streetcars peak during rush hour. Department stores peak on Saturday afternoons. If you serve all of them from the same system, their peaks and valleys partially cancel out, and your generators stay busier around the clock. So Insull aggressively pursued every type of customer. He offered cheap rates to factories. He cut deals with the streetcar companies. He even promoted electric cooking and electric irons to housewives, not because the margins were great on residential service, but because those customers used power during off-peak hours and helped fill in the valleys. And here's what's really clever. He used a declining block rate structure. The more electricity you used, the cheaper each additional unit became. This seems counterintuitive. Why would you give a discount for using more? Because of those fixed costs. Once you've built the plant and strung the wires, the marginal cost of generating 1 more kilowatt hour is relatively small. So encouraging higher consumption actually lowered the average cost for everyone. It was a virtuous cycle. Lower prices attracted more customers. More customers improved the load factor. Better load factor lowered costs. Lower costs allowed lower prices. By the early 1900s, Insull was building bigger and bigger power stations to capture economies of scale. His Fisk Street station, which opened in 1903, was one of the largest in the world. And he kept pushing for larger turbines, higher steam pressures, more efficient boilers. Each generation of equipment squeezed more kilowatt hours out of each ton of coal. The price of electricity in Chicago dropped dramatically, from about 20 cents per kilowatt hour in the 1890s to around 2 or 3 cents by the 1920s. Adjusted for inflation, that's an even more staggering decline. Electricity went from a luxury to something ordinary people could afford, and that changed everything. Now, Insull also pioneered something else that was arguably just as important: the interconnected grid. Rather than having each power plant operate as an island, he connected them together so they could share load. If one plant had a problem, others could pick up the slack. If demand surged in one area, excess capacity from another area could flow in. This required careful coordination, sophisticated switching equipment, and standardized frequencies and voltages. But the payoff was enormous. Reliability went up. The amount of reserve capacity you needed went down. And the whole system became more resilient than any single plant could ever be on its own. This is essentially the architecture of the grid you're connected to right now. Whether you're in North America, Europe, or most of the developed world, the basic structure is what Insull built in Chicago. Large central generating stations connected by a web of high-voltage transmission lines, stepping down through substations and distribution networks to reach individual homes and businesses. The specifics have evolved enormously, but the organizational logic is Insull's. He also embraced regulation, which surprises people. Most business titans of that era fought government oversight tooth and nail. But Insull actually lobbied for state regulation of electric utilities. His reasoning was pragmatic. If the government granted his company an exclusive franchise in a territory, a legal monopoly, then he didn't have to worry about competitors duplicating his infrastructure. In exchange, a public utility commission would set rates, ensuring they were fair to consumers while allowing the company a reasonable return on investment. It was a deal. The utility got stability and protection from competition. The public got reliable service at regulated prices. This regulatory compact, as it's sometimes called, became the standard model across the United States and influenced utility regulation worldwide. But here's the thing about Samuel Insull. The story doesn't end happily. Through the 1920s, he built an enormous empire of holding companies, utilities stacked on top of utilities, leveraged with debt, structured in ways that were dizzyingly complex. At its peak, his empire served over 4 million customers across 32 states. He was one of the most powerful men in America. And then the stock market crashed in 1929, and the whole edifice came tumbling down. The holding company structure that had amplified his gains on the way up amplified his losses on the way down. By 1932, his companies were bankrupt. Investors lost hundreds of millions of dollars. Insull fled to Europe, was extradited, stood trial for fraud and embezzlement. He was actually acquitted. The jury found that he'd been reckless, but not criminal, but his reputation was destroyed. He died in Paris in 1938, largely forgotten, with less than $1,000 in his pocket. His collapse had enormous consequences, though. The public outrage over the Insull debacle was a major driver behind the Public Utility Holding Company Act of 1935, which broke up the giant utility empires and established strict federal oversight of interstate electricity companies. It also helped build support for one of the most ambitious electrical projects in American history: rural electrification. Because here's something that's easy to forget. Even by the early 1930s, with Insull's model having transformed urban America, roughly 90% of rural American farms still had no electricity. The private utilities had done the math and concluded it wasn't profitable to string lines out to remote farmsteads where customers were few and far between. The load density, the amount of electricity consumed per mile of power line, was just too low to justify the investment. So while city dwellers enjoyed electric lights, refrigerators, and radios, farm families were still using kerosene lamps, hand pumps, and ice boxes. The gap between urban and rural life was enormous, and electricity was a big part of why. The Rural Electrification Administration, created in 1935 under Franklin Roosevelt's New Deal, changed that. The REA didn't build power lines itself. Instead, it provided low-interest loans to farmer-owned cooperatives, which then built and operated their own distribution systems. It was an elegant solution. The cooperatives were non-profit, so they didn't need to generate returns for shareholders. The federal loans gave them access to capital they could never have raised on their own. And the farmers themselves had a stake in making it work because they owned the system. The results were staggering. In 1935, about 11% of American farms had electricity. By 1950, it was 90%. In just 15 years, an entire way of life was transformed. Farm wives, and it's worth noting that the burden of pre-electric farm labor fell disproportionately on women, suddenly had electric water pumps, washing machines, refrigerators, and lights. The sheer physical drudgery of rural life was reduced dramatically. Farmers could use electric milking machines, grain dryers, and workshop tools. Productivity soared. Rural communities got access to radio and later television, connecting them to the broader culture in ways that had been impossible before. And this transformation wasn't unique to America. Across the world, throughout the 20th century, electrification was one of the most powerful drivers of economic development and quality of life improvement. The Soviet Union under Lenin famously declared that communism was Soviet power plus electrification of the whole country, and launched massive campaigns to bring power to rural areas. Britain established its national grid in the 1930s, connecting regional power systems into one unified network. Country after country followed the same basic pattern: centralized generation, high-voltage transmission, regulated distribution, and the steady extension of service to ever more remote areas. But as the grid grew larger and more interconnected, it also grew more complex, and new kinds of problems emerged. Problems that the pioneers couldn't have anticipated. Because when you connect thousands of generators and millions of consumers into a single synchronized network, you create something that behaves almost like a living organism. And like any organism, it can get sick in ways that are hard to predict. The most dramatic example of this, the event that really forced engineers and policymakers to reckon with the fragility hidden inside the grid's apparent strength, happened on a cold November evening in 1965, when a single relay tripped at a hydroelectric station near Niagara Falls, not far, actually, from where Tesla and Westinghouse had built that first great AC power plant 7 decades earlier. A single protective relay, set to a threshold that had been configured years before and never updated as loads grew, sensed that power flowing northward into Canada on one of the transmission lines had exceeded its limit. So it did exactly what it was designed to do. It disconnected that line. And that's the thing about cascading failures. Every individual component does exactly what it's supposed to do, and the result is catastrophe. When that first line tripped, the power it had been carrying didn't just vanish. It redistributed itself across the remaining lines, the way water finds new paths when you block a stream. But those remaining lines were already carrying heavy loads. It was early evening. People were getting home from work, turning on lights, cooking dinner. The grid was near its daily peak. So now those lines were overloaded too, and their protective relays tripped. One by one, in a chain reaction that took only about 5 seconds, all 5 of the main transmission lines connecting the Niagara generating complex to the rest of the network disconnected. And suddenly, a huge amount of generation was cut off from the consumers who needed it. What happened next is a lesson in the physics of synchronized AC grids. Remember how we talked about alternating current? How all the generators on the grid have to spin in lockstep, maintaining the same frequency. When generation and consumption are balanced, the frequency holds steady at 60 cycles per second. But when you suddenly lose a big chunk of generation, there's more demand than supply, and the remaining generators start to slow down under the extra load. The frequency drops. And when frequency drops, protective systems at power plants start tripping those generators offline too, because running a turbine at the wrong frequency can physically damage it. So you lose more generation, which causes more frequency drop, which causes more generators to trip. It's a vicious spiral, and it can happen terrifyingly fast. Within 12 minutes of that first relay tripping near Niagara, 30 million people across the northeastern United States and Ontario, Canada, were in the dark. New York City, Boston, Rochester, Hartford, all blacked out. The area affected covered 80,000 square miles. And here's what makes it so humbling from an engineering perspective. Nothing was actually broken. No generator had failed. No transmission tower had fallen. No storm had knocked anything down. The physical infrastructure was perfectly intact. The system had been brought down by its own protective mechanisms, by the very devices designed to keep it safe, because the interactions between those devices at the scale of this enormous interconnected grid produced behavior that nobody had fully modeled or anticipated. People were trapped in elevators and subway cars. Traffic signals went dark across Manhattan. Hospitals switched to emergency generators. About 800,000 people were stuck on the New York subway system. And yet, and this is one of those details that tells you something nice about people, the blackout was remarkably peaceful. There was very little looting or disorder. Neighbors helped neighbors. People directed traffic. There's a famous, probably apocryphal story that the birth rate in New York City spiked 9 months later, though demographers have pretty thoroughly debunked that one. But the real legacy of the 1965 blackout was institutional. It forced a reckoning. the electrical engineering community realized that the grid had grown into something whose behavior they didn't fully understand. You could model individual generators, individual transmission lines, individual relays, but the emergent behavior of the whole system, with all its feedback loops and non-linear interactions, was beyond what anyone had rigorously analyzed. In response, the utility industry created what eventually became the North American Electric Reliability Corporation, or NERC, an organization dedicated to studying grid reliability and establishing standards to prevent cascading failures. The whole field of power systems stability analysis grew enormously after 1965. Engineers developed better computer models, better monitoring systems, better coordination protocols between utilities. And yet, and this is the part that's almost poignant, the grid blacked out again. In 1977, New York City went dark again, this time after lightning struck transmission lines in Westchester County. And that blackout was very different from 1965. Widespread looting, over 1,000 fires, more than 3,000 arrests. Same city, same grid failure, completely different social response, largely because the economic conditions were so different. The city was in fiscal crisis, neighborhoods were struggling, and the darkness became an occasion for anger that had been building for years, which reminds you that the electrical grid isn't just an engineering system. It's embedded in a social and economic context, and you can't fully understand its failures without understanding that context. The biggest blackout in North American history came even later, August 14, 2003, and the pattern was eerily similar to 1965, just at a larger scale. It started in Ohio, where a combination of high demand on a hot summer afternoon, some transmission lines sagging into overgrown trees, and, critically, a software bug in the alarm system at the control center of a utility called First Energy meant that operators didn't realize they were losing lines until it was too late. The cascade spread across 8 states and a Canadian province. 55 million people lost power. Some areas were dark for up to 4 days. 11 people died. The economic cost was estimated at somewhere between $6 and $10 billion. Think about that for a second. A software bug, trees that hadn't been trimmed, and the result was the largest blackout in North American history. The grid, for all its incredible sophistication, this machine that hums along so reliably that we barely think about it, is always just a few failures away from cascading collapse. And the reason is fundamental to its architecture. It's that synchronization requirement. Every generator on the grid, spinning in lockstep, frequency locked together. It's what makes AC power transmission work so beautifully, but it's also what makes failures propagate. When one part stumbles, the whole organism feels it. Now, this might sound like the grid is badly designed, but it's really not. It's actually a remarkable achievement. The North American grid has been called the largest machine ever built by humanity, and it delivers power with a reliability that would have seemed miraculous to someone like Insull, let alone Faraday. The lights stay on, in most places, more than 99.9% of the time. The fact that we're surprised when the power goes out, that we treat it as news, is itself a testament to how well the system works. But the blackouts reveal the tension at the heart of the grid's design. Interconnection makes the system more efficient and more resilient against small disturbances, but it also creates pathways for large disturbances to propagate. It's a trade-off, and managing that trade-off has been one of the central challenges of electrical engineering for the past half-century. And this brings us to something that's been quietly transforming the grid in ways that are just as profound as anything Insull did, or Edison, or Tesla. The rise of electronics, specifically power electronics and digital control, has been reshaping what the grid can do and how it operates. See, for most of the 20th century, the grid was essentially an analog system. Generators spun, current flowed, and control was achieved through mechanical switches, analog relays, and human operators watching gauges. But starting in the 1960s and accelerating dramatically from the 1980s onward, solid-state electronics began to infiltrate every level of the power system. The key device here is something called a thyristor, and later, its more advanced descendants, IGBTs, which stands for insulated gate bipolar transistors. These are semiconductor devices that can switch enormous amounts of electrical power on and off thousands of times per second. And that capability turns out to be transformative because it lets you do something that was essentially impossible with the old electromechanical technology. You can convert between AC and DC freely. You can control the flow of power with precision, and you can do it all fast enough to respond to disturbances in real time. One of the most important applications is high-voltage direct current transmission, or HVDC. Now you might find this ironic. After all that drama with the current wars, after AC won so decisively, here we are bringing DC back. But it makes perfect sense. For very long distances, or for underwater cables, or for connecting grids that operate at different frequencies, DC transmission turns out to be more efficient than AC. The reason is that AC transmission lines have what's called reactive power losses. The alternating electromagnetic fields interact with the line itself, wasting energy in ways that get worse over long distances. DC doesn't have that problem. A DC line just pushes current steadily in one direction. The catch, back in Edison's day, was that you couldn't easily convert DC to different voltages. But power electronics solve that. Modern HVDC converter stations use massive arrays of thyristors, or IGBTs, to convert AC to DC at the sending end. Transmit it hundreds or even thousands of miles at very high voltage, sometimes 800,000 volts or more, and then convert it back to AC at the receiving end. China has built enormous HVDC lines, some stretching over 3,000 kilometers, carrying power from hydroelectric dams in the interior to the booming cities on the coast. Brazil uses HVDC to bring power from the Itaipu Dam to São Paulo. There are HVDC cables running under the English Channel, under the Baltic Sea, connecting Scandinavia to continental Europe. And here's what's particularly elegant about HVDC links in the context of grid stability. They act as firewalls. Because the DC link doesn't require the generators on either side to be synchronized, a cascading failure on one grid can't propagate through the DC connection to the other grid. It's like having a controlled gateway instead of an open door. So in a way, the modern grid is becoming a hybrid. AC networks for regional distribution, because AC is still the most practical technology for that, connected by DC links for long-distance transmission and for isolation between regions. Tesla and Edison, reconciled at last, each technology doing what it does best. But power electronics didn't just change transmission. They changed everything downstream too. The devices in your home, in your office, in factories, they increasingly don't want the raw AC power that comes out of the wall. Your laptop, your phone charger, your LED lights, your television. They all contain power electronic converters that transform that AC into precisely regulated DC at whatever voltage the device needs. The little black box on your laptop charger cable? That's a switch-mode power supply, a marvel of power electronics that converts AC to DC far more efficiently than the old heavy transformer-based adapters. It switches the current on and off tens of thousands of times per second, using that high-frequency switching to step the voltage down through a tiny transformer that can be a fraction of the size and weight of the old ones. And this proliferation of electronic loads is actually changing the character of the grid itself in ways that engineers are still working to understand. All those switch-mode power supplies and variable speed motor drives and LED dimmers, they draw current in little pulses rather than smooth sine waves, injecting harmonics into the grid, distorting the clean 60 Hz waveform that generators produce. Managing those harmonics, keeping the power quality clean enough for sensitive equipment while accommodating billions of nonlinear electronic loads, is one of the quieter but genuinely important challenges of modern power engineering. And then, of course, there's the transformation that's been dominating the conversation about electricity for the past couple of decades. The shift in how we generate power in the first place. For over a century, the basic model was the one Insull perfected. Big central power plants burning fossil fuels or splitting atoms, sending power outward through the transmission and distribution network to passive consumers. But now, increasingly, generation is becoming distributed and variable. Solar panels on rooftops, wind farms spread across hundreds of square miles. And these sources have a fundamentally different character from the big spinning generators that the grid was designed around. A coal plant or a nuclear plant produces steady, controllable, predictable power. The sun and the wind do not. They produce power when nature decides, not when the grid operator needs it. And they don't spin massive turbines that naturally maintain frequency through their rotational inertia, that physical momentum that acts as a buffer, keeping the grid stable during momentary imbalances. Integrating large amounts of renewable generation into a grid designed for centralized, dispatchable power plants, that's one of the great engineering challenges of our time. And it's a challenge that touches everything we've talked about. The physics of AC synchronization, the economics of load management that Insull figured out, the stability concerns that the blackouts revealed, the power electronics that enable new forms of control. Engineers are working on grid-scale battery storage, on smart inverters that can mimic the behavior of spinning generators, on demand response systems that adjust consumption to match variable supply, on continent-spanning transmission networks that can move solar power from where the sun is shining to where it's not. It's a problem that requires every tool in the electrical engineer's kit, and some tools that haven't been invented yet. And at the heart of all of it, at the heart of the blackouts and the HVDC lines and the smart grids and the renewable integration challenge, is something that would have been deeply familiar to Michael Faraday, standing in his basement laboratory at the Royal Institution nearly 200 years ago, spinning a copper disc between the poles of a magnet, the fundamental relationship between electricity and magnetism, the movement of charges through fields, the invisible dance of electrons that somehow powers everything we see, everything we touch, everything we've built. That dance is still the same one Faraday glimpsed when the needle of his galvanometer twitched. That tiny, almost apologetic flicker that told him a moving magnetic field could push electrons through a wire. And from that single observation, that one quiet moment of noticing, came the entire electrical world. Think about the arc of that story for a second. Think about how far we've traveled tonight. We started with Thales of Miletus, rubbing amber against fur somewhere on the coast of what's now Turkey, 26 centuries ago, watching bits of straw leap toward the stone as if pulled by something invisible. He didn't know what he was seeing. Nobody did. It was a curiosity, a parlor trick, a footnote in a philosopher's catalog of the natural world. And for 2,000 years, that's basically where it stayed. Static electricity, a mystery without a framework, without even the right questions to ask about it. Then came Gilbert, carefully distinguishing magnetic attraction from electrical attraction, giving us the word electric itself. Then Gray, discovering that this strange influence could flow through some materials and not others, that there were conductors and insulators, that electricity could travel. Dufay, showing there were two kinds of charge. Franklin, unifying those into a single fluid model, positive and negative, and then, with extraordinary courage or extraordinary recklessness, depending on how you look at it, proving that lightning was electrical. The Leiden jar, Galvani's twitching frog legs, Volta's pile, giving us the first steady current. Ørsted's compass needle deflecting near a wire, Ampere's mathematics, Faraday's spinning copper disc, each step building on the last, each one impossible without what came before, and each one opening a door that the previous generation couldn't even see. And here's what strikes me about all of it. Lying here in the quiet, thinking back over the whole sweep of this history, the thing that ties it all together isn't just the physics, it's the people. It's the fact that at every single turning point, there was a specific human being who noticed something, or wondered about something, or refused to accept the conventional explanation. Faraday, the bookbinder's apprentice with almost no formal education, who saw deeper into the nature of electromagnetic fields than anyone alive. Tesla, the insomniac visionary, who could build a motor in his mind before he ever touched copper wire. Insull, the English immigrant who figured out that the economics of electricity were just as important as the engineering. The lineman who climbed poles in rural Alabama to bring light to farmhouses that had never had it. The relay engineers who spent years after the 1965 blackout redesigning protection systems so that one failure wouldn't cascade into 30 million people sitting in the dark. These are all real people who made real choices, and the world you live in, the one where you can flip a switch and light appears, where you can plug in a phone and it charges, where a hospital's ventilators keep breathing for patients who can't breathe for themselves, that world exists because of those choices, because someone was curious, because someone was stubborn, because someone saw a problem and decided it was their problem to solve. And now, in our time, the choices are different, but the stakes are just as high, maybe higher, because the electrical grid that powers modern civilization is being asked to transform itself in ways that would have seemed impossible even 20 years ago. The challenge of integrating renewable energy isn't just a technical puzzle. It's a reimagining of the entire philosophy of how we generate and distribute power. For over a century, the model has been fundamentally the same. Big power plants in fixed locations, burning fuel to spin turbines, sending electricity outward through a hierarchical network to passive consumers. Supply follows demand. The grid operator watches the load rise and fall throughout the day and dispatches generation to match. That's the Insull model, refined and computerized and scaled up, but recognizably the same idea. Renewables flip that model on its head. With solar and wind, you don't get to decide when to generate. The sun rises and sets on its own schedule. The wind blows when it blows. So instead of supply following demand, you increasingly need demand to follow supply. or you need storage to bridge the gap. And that's a profound shift. It changes the economics, the engineering, the control systems, the market structures, everything. Grid-scale battery storage is one piece of the puzzle, and it's advancing fast. Lithium-ion batteries, the same basic chemistry that powers your phone, are being assembled into massive installations, some of them the size of several football fields, that can absorb excess solar power during the middle of the day and release it during the evening peak when the sun is going down, but everyone's coming home and turning on their air conditioning. The Hornsdale Power Reserve in South Australia, which went online in 2017, was one of the first large-scale demonstrations that batteries could respond to grid disturbances faster than any conventional power plant, in milliseconds rather than seconds or minutes. It proved that batteries weren't just storage, they were stability tools. And since then, installations have gotten bigger and cheaper. But batteries alone aren't enough for the kind of long-duration storage you need to handle, say, a week of cloudy, windless weather. That's where other technologies come in. Pumped hydro, where you pump water uphill when you have excess power and let it flow back down through turbines when you need it, which is actually the oldest form of grid storage and still the largest by total capacity worldwide. Compressed air storage. Hydrogen produced by electrolysis. Each has trade-offs in efficiency, cost, geography, and scale. And then there's the grid itself, the transmission network. Remember, one of the fundamental advantages of AC power, the reason Tesla and Westinghouse won the current wars, was that transformers let you step voltage up for long-distance transmission and back down for local distribution. That's still true. But the modern grid needs to move power over distances that even the pioneers of AC didn't envision. If you want to balance solar generation across an entire continent, harvesting sunlight from the southwest and sending it to the northeast, or from the Sahara to Scandinavia, you're talking about transmission distances where even AC lines lose too much power to resistance. And that's where HVDC comes back in. Those high-voltage direct current links we talked about, using power electronics to convert AC to DC and back again. The irony is delicious, isn't it? Edison's direct current, banished from the grid over a century ago, is now essential to the grid's future. Not for the last mile to your house, AC still wins there, but for the long-haul superhighways that connect renewable generation zones to population centers. China has built some of the most ambitious HVDC lines in the world. The Changji-Guquan link, energized in 2019, runs over 3,000 kilometers at plus or minus 1,100 kilovolts, transmitting 12 gigawatts of power from wind farms in Xinjiang to the eastern seaboard. 12 gigawatts. That's roughly the output of 12 large nuclear power plants flowing through a single transmission corridor. The power electronics required to make that work, the converter stations at each end, packed with thyristors and IGBTs switching thousands of times per second, represent some of the most sophisticated electrical engineering on the planet. And it all traces back to the same fundamental principle. A changing magnetic field induces a voltage in a conductor. Faraday's law, scaled up to continental dimensions. But here's maybe the most fascinating part of the modern grid transformation, and it's something that connects back to the very earliest days of our story. The smart grid, the idea that the electrical network should be not just a passive delivery system, but an intelligent, responsive, self-healing organism, is essentially giving the grid a nervous system. Sensors everywhere, communicating in real time, measuring voltage and current and frequency at thousands of points across the network. Algorithms that can detect a disturbance and reroute power in milliseconds. smart inverters on rooftop solar panels that can adjust their output to help stabilize local voltage, electric vehicles that can charge when power is cheap and plentiful and even feed power back into the grid when it's scarce, your washing machine talking to the grid and deciding to run at 2 in the morning when wind power is abundant and electricity prices are lowest. It sounds futuristic, but pieces of it are already here. And what it really represents is the electrification of information itself, using data and computation to manage the flow of electrons more intelligently, which brings us full circle in a way that feels almost poetic, because electricity and information have been intertwined since the very beginning. The telegraph, remember, was one of the first practical applications of electrical science. Samuel Morse sending "What Hath God Wrought" from Washington to Baltimore in 1844. That was electricity carrying information. And now information is being used to manage electricity. The two have become so deeply entangled that you can't really separate them anymore. The internet runs on electricity. The electrical grid increasingly runs on the internet. Each enables the other in this beautiful recursive loop. And all of it, every single bit of it, still comes down to electrons moving through conductors under the influence of electromagnetic fields. The physics hasn't changed. Maxwell's equations, written down in the 1860s, still describe everything that happens in the most advanced smart grid, in the most sophisticated power electronics, in the HVDC line stretching across a continent. What's changed is our ability to harness those equations, to build systems of staggering complexity that exploit the behavior of electrons with ever greater precision and ever greater scale. So as you lie here, maybe drifting a little, maybe already half asleep, think about the room you're in. The walls around you are threaded with copper wire, probably 12 or 14 gauge, sheathed in plastic insulation, running through the studs and joists like veins through a body. Those wires connect to a panel in your basement or your closet, and that panel connects through a meter to the distribution lines outside, and those lines connect to substations, and the substations connect to transmission towers marching across the landscape, and those towers connect to power plants and wind farms and solar arrays and battery installations, and all of it is humming right now, at this very moment, at 60 hertz, or 50, depending on where in the world you are, synchronized across thousands of miles, millions of generators, and loads rising and falling together in a vast, invisible, electrical heartbeat. And that heartbeat started with amber and fir, with a philosopher's curiosity about why straw jumped toward a rubbed stone, with a court physician carefully cataloging which substances could be electrified, with a retired dyer discovering that electricity could flow through a thread across his garden, with a professor in Italy watching a dead frog's leg kick, with a professor in Denmark noticing a compass needle twitch, with a self-taught bookbinder spinning a copper disc and watching a galvanometer needle move, just barely, just enough. That's the story of electricity. It's a story about curiosity, about patience, about people who looked at something everyone else ignored and asked, what if? What if that tiny spark means something? What if that faint deflection matters? What if I could make it bigger, make it useful, make it light up a city? And the beautiful thing is, the story isn't over. It's still being written right now by engineers and scientists and inventors working on problems we've talked about tonight: grid stability, renewable integration, energy storage, power electronics, and on problems we haven't even imagined yet. The fundamental mystery that Thales noticed 2,600 years ago, that strange attractive force hiding inside a piece of amber, still has secrets to reveal. We understand so much more than he did, more than Franklin did, more than Faraday did, more than Tesla did. But the universe is generous with its puzzles, and electricity, this invisible, silent, impossibly fast movement of charge, still has the power to surprise us. For now, though, the current flows. The grid hums. The lights are on or off, depending on your preference. And the electrons in the wires around you are doing their quiet, tireless work, just as they have since long before anyone thought to put them to use, flowing, spinning, dancing to the tune of fields that permeate everything, everywhere, always. It's a good thing to fall asleep to, I think. The knowledge that this enormous, intricate, improbable system is holding steady through the night, keeping the world running while you rest. 60 cycles per second, 1 billion electrons drifting through copper. The legacy of every curious mind we've met tonight.